So the presentations are out on the usual link. There was a little bug in it. If you refresh, you should get a clean image. And please feel free to download them. You're going to be able to present as we go, CJ.
I'll start there. I'll set up some discussions. There are going to be other presenters too.
Good. And I am recording, so we'll have it up on the website before the end of the day for people who want to pass on the information.
Great. All right, I think we probably have critical mass. Can we go ahead?
Yeah, let's do that. We got about 15 on, and there'll probably be a few more as we go, but let's get it kicked off. Thanks, CJ.
All right. So the topic today was support for hierarchical decomposition. And so in a side set of meetings that we have, we've been working through some specific issues and trying to look at specifically when people are trying to do things hierarchically, and among the things that they're trying to do are to decompose the data and potentially match the work that needs to get done to the target platform or a particular subset of resources. How does that work, and what infrastructure do you want to be able to support that? And so that's essentially the topic today. So let's consider this kind of a working session rather than sort of completed work. I'm going to start with a simple example here. I jumped into slide 12 of the linked file, and let's just kind of consider some different roles. One is an agent. Up at the top here, we have two agents. One is a work creator, and another is a scheduler. This is in the spirit of a separation of concerns. You have one agent who says, I'll tell you what work needs to be done. In this case, what the tasks are and the dependencies are. All right, this is the output of that. And then down here in the green layer, is there a question or comment? Okay. Down here in the green layer, you have sort of infrastructure, which represents the graph, and in that graph, resources may not yet be bound. And then that goes up to the scheduler, and the scheduler figures out where, when, and how. Where that does the binding based on some cost model of, hey, I can get it done faster over here than over there, or this resource is available while that one's busy. Potentially what order things are going to happen in. I could do this for locality. Let's add that note. And then there's a question of how. And if you go and map this to a particular target, so for example, if you started out with an assumption everything's going to happen on the CPU, then you didn't need to do any additional management of your data because it's all there in the CPU. If you were going to offload that to some other accelerator, then you may need to do allocation and freeze of temporaries. You may need to move data back and forth. You may need to do additional synchronization, and you may have other additional coordination. So to that end, as you make your binding decisions as to say, do this work there, then that may imply additional effort that's required that would be represented by a graph node to accomplish that work. And again, then you may pass that down to a plumbing layer that would serve as implementational infrastructure, where given, do an allocation, but do it in using a function pointer that works on this particular target and that uses that particular kind of memory. And at the semantic layer, you don't care about exactly how it's done, and you can leave that to an expert to over time refine sort of how that works, and to be able to change out and offer improvements to the plugged in functionality per target. So this is nothing new here. This is exactly what we've been talking about, but I wanted to set this up for symmetry with respect to a more complicated case. So any questions or comments here? Okay, motherhood and apple pie. Had an apple fritter this morning, which is delicious. Okay, so the work creator, again, knows what to do in which data, and in this simple case, they might go through the nodes in a graph and identify those that are retargetability candidates, like, hey, for this particular node, the user gave me a task handle for either this target or that target, so I have a choice. And so then you may need to say, well, that particular node could execute on either of these resources. So here's a superset of resources that the node in the graph could be bound to. And then there's a set of plugged-in implementations that are relevant to cover those targets. So maybe I have, I'm constrained in this particular case for some reason to use only 2 of 3 targets, even though I have reference implementations for 3. So I'll just say, okay, only keep around the 2 that are interesting and relevant. And then when it comes time to sort of issue this work, it picks which of those it's going to do based on, and actually call through this infrastructure on the right-hand side based on which execution resources, based on which choice of implementation. So in this case, I could have an allocator, and I could have a couple different flavors. I could have a thread local storage one. I could have a same size allocator. So you may want an extra chooser there. And then you could get back in something that says, well, for that particular set, here's something that describes the resources enough. And here's a policy blob as to how I would want that to get executed. So that might be, as earlier slides that I skipped over could describe, I might describe a grid in block in 3 dimensions for a GPU, or it just might be OMP num threads for OpenMP or something like that. And then I have the task handle. So this is basically, at this point, at the point of work creation, I'm specifying enough in a parameterized way that a scheduler can choose from among a palette of options that have been exposed. And the scheduler then makes the binding decision, refines a set of tools to cover just the subset of entries that's relative to the bound targets, and then can actually issue the work. So the work creator and the scheduler in this model, the work creator sets up everything and creates the opportunity up front, and the scheduler chooses only from what the work creator has exposed to it. Again, some separation of concerns. So any comments or questions there? All right. So we could make that more interesting, because in addition to just saying, here are the ways that you would execute on some set of resources where the scheduler is going to decide later, the when and the where and the when and how, you could also provide additional information. You could say, well, you may end up making hierarchical decisions, hierarchical decomposition decisions later. So given the data size, given a function which knows how to do data partitioning, and given a function that knows how to break it up into do work just in case you're going to decompose the work more, and we'll give an example of that in a bit, I'll give you all that, as if, what if information as a work creator, and pass that through the infrastructure down to the scheduler. And then the scheduler takes that information and again makes these binding, ordering, and transformation decisions of its own and plugs that in below. Okay, so you can imagine a scheduler which could get increasingly sophisticated. So using the same color scheme of the blue, yellow, green here, the scheduler could do just binding decisions only, right? That was the first example of where it says, give me a node and I'll figure out what to, which target to bind it to. And something we also alluded to in that first case is that you may need to add additional nodes for data management or movement. You may need to alloc or free or move some data around depending on the target and how memory looks and whether data is shared. But you could also say, hey, I want to expand that graph. I want to tile it and create a whole bunch more nodes depending on the degree of tiling to get things down to an appropriate tile size for the target. And maybe even the tile sizes are different for each of the different nodes. Maybe I could have compute tile sizes, I could have communication tile sizes. And so I could essentially use target-specific parameters to drive the creation of the graph. Like I could say, I want a tiling degree of 4 or of 16 or whatever else. And I could also choose at this point to add data transformation nodes. I might do a transpose or a reduction or a compression. And so depending on how it is that we're going to partition the data, there may be other those kinds of more trivial and straightforward changes to the data, actions on the data to do that. And that's all just based on the target. You could actually, the next level of complexity is that you could base it on the data. You could look at the characteristics of the data and say, well, I've got a matrix, but it's a banded matrix, or I have a tensor, but it's especially sparse, and so I'm going to do something different based on my knowledge of that. Or I may realize that in the middle of doing AMR, whoa, I'm running out of memory, and so I need to do something different to be able to not get killed off, and so may I adapt in that way. So these are some of the different sort of extents of richness, aka complexity, that you could apply in trying to do some scheduling. So there's, if I'm going to try to do parameterized decomposition, you could have questions of the timing of the decomposition. It could be static and completely known ahead of time, so I just create the graph from the start. Or it could be partly static and partly dynamic, where the graph is generated as a function of some parameters not known until after the initial graph is constructed and submitted. For example, based on the target topology, the resource availability, the data, and AMR is an example here. And Mike Bauer has a really nice presentation to talk about some of that stuff here a little bit later. So there are really two types of decomposition. One is the data partitioning, and another is the work decomposition. And there are different grades of these that I could think of, and encourage you to just go ahead and edit and add some more of these or whatever. There's a trivial where you do the same thing on every data element. So I think that's true of a matrix multiply. It could be pre-partitioned and arranged in a hierarchical way, like maybe an octree, so that that's fairly obvious as to how you would do it. Or you could do more action at runtime and have a runtime repartitioning, for example, based on transpose or reduction. And if maybe you're going to recursively decompose it, and the degree of recursion could be fixed or it could be target specific, or you could specify a criteria that says, hey, just keep decomposing it until you get to a tile size that's appropriate for that particular target. And as a user, you don't necessarily have to be forced to pick when you don't know. You don't have a clue, and you don't know what that should be for a machine that hasn't even been invented yet at the time that you write your code. And similarly, the work decomposition could be trivial, or you could just be transforming data, or you could generate work, like a tiled Zaleski. So let's look at this Zaleski example. I think we're all pretty familiar with this code in this example, and the graph that represents it on the right. So if you look at this, a particular visitation order has been prescribed in this code. K is increasing, M is increasing, N is increasing. So it's, I think you call this left to right, right? So that could be decided for you and baked in, or you could describe it in this way, thanks to Piotr, where you just say what needs to happen, and you can still infer the data dependencies based on the lexicographic order here. But given that each of these things are sort of independent of one another, they could be done in any order. And so something else, like a scheduling agent, could further describe to overlay a scheduling order on top of this. So this is essentially what is in this box could be passed in as essentially an ASCII string by the work creator and interpreted by the scheduler to say, oh, I know what a TRSM is, and I know what to do with it, and I know what an if statement is, and so on, that it could use to interpret this. So this is an example of where this is going to be different for Cholesky than it is for QR, than it is for whatever else. And so if an infrastructure wishes to, instead of hard coding this, to say, well, here's how that could be expressed in an ASCII string, and it's worth being able to add the complexity instead of just hard coding it to make it more general and let it be interpreted, then you could describe it this way, pass it through the infrastructure, and use this approach. So again, here you're putting this work generation function like what we just looked at, and potentially a data partition function, passing it through the hierarchical infrastructure down to the scheduler. The scheduler does its thing, and it may do this iteratively. That's what the dotted line is about, as you go further and further down the recursive layers of the hierarchy. Okay, does this make sense so far? So as we have had some discussions about this, we kind of, this is an imperfect description of this, you could think of, from a data perspective, you can either have no partitioning or really trivial data partitioning, or something more serious. And you can have essentially a fixed static graph with no graph generation, where you could do it just for data transformation or graph generation, or you provide a graph generation function like we just had. And so some examples of this are of what doesn't need any special handling as matrix multiply. Of something that could use this is hierarchical tensors, like octrees or a hierarchical mesh. And Dimitri, you talked about potentially some of the transformations that are relevant in an exotensor context are these. Mike, you talked about some of the ones that are relevant for AMR are these, and Piotr, these for slates. So let's pause here for comment and adding anything else that people see in this as additional examples. Don't make me do all the talking. So is this clear? Any other questions on sort of what it is that we're talking about and why this might be interesting? All right, I'll say a little bit more and I'll turn this over to some other folks. So essentially, there's the reason why this conversation could get interesting is to ask, what is it that we do today? What are the trends as we add sort of greater richness, and how could infrastructure help? And where, who could start to use this, and what do you actually need to be able to make that useful and work? So some trends that we could see are in data partitioning that you can start with essentially none to hard-coded to here's a predefined palette of choices for some of the partitioning functions that you could pick from, and Dimitri identified exotensor as being in that place. Or you could do user-defined. Mike, is this how you would describe the Legion mapper? Where would you put that along here?
Yeah, so I would say that the Legion mapper is sort of, it doesn't go in the data partitioning because Legion has its own application level dependent partitioning API, but the application mapper is what decides where the actual copies of subregions and stuff get placed in the memory hierarchy. So I guess
so
the map, think of it as the Legion decouples the computation of the partitioning from the choice of where the actual data gets placed. Right, and the Legion mapper is what actually gets to decide where things get placed.
Okay, so you would, that's about placement rather than
partitioning, yes.
Than partitioning.
Yeah.
So we'll just take that out.
Right, you actually want those two things decoupled, right? Your choice of how you partition data is often, not necessarily how you want to actually place it.
Yeah, fair enough. I'll let that comment here. And Legion manages the placement and asks the user to do the partitioning. Right?
That's correct, because in general we tend to find that, and I think this is true in most cases, is that partitioning is a really, really hard problem, right? And often is application domain specific, right? And it seems unreasonable to expect a system to be able to make perfect partitioning decisions in all possible cases, because the range of machines and applications you want to target is too large for any system to get it right in all the cases. And so instead you push that up to the application to decide, what is the partitioning algorithm you want to use, but then still give the user and the mapper control over how data gets placed once it's been partitioned.
Well, maybe you would still put it this way to say, in this next progression, it's from the user does it totally, and the infrastructure doesn't have much to do with it, or the user controls the data partitioning parameters.
That's right.
Like you have a fixed degree of recursion that the user specifies, or maybe they have a different degree of recursion per target, or and so they're being prescriptive about what should happen in that case, or they're being descriptive in this next case of where you basically say, here are the conditions that I want you to achieve. Like, please go until you get to a tile, keep recursing or keep partitioning until you get to a tile size that's suitable for each respective target. And the run, and here's how to do the partitioning. And then the runtime iteratively recursively applies that until you get to the right size there.
Yeah.
So would you have put Legion in this first one or the second one?
Well, let's see. I mean, it has to kind of go in both. I think Legion is more in the first one where we sort of provide a generic partitioning API. And I think, there's sort of two styles of partitioning that we see users using in Legion, which I think is instructive, which is that one is the style of partitioning that you were describing, which is the sort of tiling-based approach, which happens a lot for structured data, right? Where you want to recursively decompose, your array or whatever down into smaller and smaller tiles, depending to sort of match your memory hierarchy. And like this is a very Sequoia-like idea where like you want to recursively partition that way. I think the other kind of partitioning that we see users using much more recently and much more frequently has been sort of the unstructured partitioning, where you have to partition up your graph or your mesh or some other data structure which doesn't necessarily tile in a natural way. And that's a little bit harder one to parameterize the way I think you're describing, because oftentimes the way you partition that is often with like Parmetis or some other hypergraph based partitioning algorithm, and it's I think those ones are much harder to parameterize. I think it's really natural to parameterize the tiling based ones, but the more general partitioning scheme for unstructured data structures is a little bit harder to sort of put into a or to pull out the parameters as you were describing.
Mm-hmm. Okay.
And so we try to support both.
Would you say that this is this last case that is something that you can see Legion going to, or no?
When you say the last case, you mean the graph generation one?
No.
No. Okay.
This one.
Let's see. You mean? Oh, I see. I can imagine. What I would imagine is someone actually building a partitioning library on top of Legion to do that. I don't think we have any ambition to actually bake in the partitioning logic into Legion itself. I'm not sure that we gain a whole lot by doing that. But you know, we certainly have been encouraging people to build partitioning libraries on top of Legion. And so, for example, right now, you know, we have a little bit of work at Los Alamos where people are trying to sort of have Legion interoperate with Parmetis, but you know, there's no reason that Parmetis couldn't actually be built on top of Legion, because like the algorithms that Parmetis employs to compute its partitions, right, are often, you know, they're sort of agnostic to the underlying programming model that you're using, and so like I think the way that I foresee, you know, people building partitioning or doing partitioning in the future in Legion is more of a library-based approach where Legion provides the primitives for doing the partitioning, but then the libraries themselves, you know, provide the algorithms for deciding how to partition up, you know, your graph or your mesh or even your array. Especially, you know, sparse arrays are much harder, but dense arrays obviously doing pretty traditional tiling and stuff like that.
Okay. All right. Any other additions to this? Comments for other things? You want to comment here on Slate a little bit, Piotr?
Sure. I mean, it's we have in Slate the data decomposition. We are bound by the fact that a lot of people right now on these large installations use Scale APAC, and they already know how to deal with the Scale APAC data decomposition, which is 2D block cyclic. So Slate has to catch all this functionality and provide that. So that's where the partitioning. We have a lot of code that reads it from a file and do all kinds of manipulations that involve this 2D block cyclic, but we also provide through the C++ mechanism of iterators to have a little bit more custom data distribution. And perhaps this could be extracted and kind of become more of a graph computation. Right now, we just do it through just regular C++ iterators. So that's data partitioning, and for graph generation, in a way, it's for us, it's how we write the loops right now. But if we just compress these loops into iterators, that could be more of a more abstract thing and turn it into more of a visitor pattern. So that's the data partitioning and graph generation in Slate.
Okay. So I'm going to pick on a couple other people. Vinay, I know that you've been looking at this in the abstract. Have you thought you kind of represent a completely different set of graphs and interest there? Have you considered the relevance that this might have for you?
I think for us, the problem, our earlier speaker for Legion, what he mentioned about, you know, it's very difficult to partition the graph. So we are viewing mostly from the graph perspective, and can it be pre-partitioned? It's very difficult to say, and having a predefined palette could be a start, but is it optimal? We don't know yet.
Okay. Okay, and what can I see? Other folks from RNL, Yingwei, Weil. David,
Sorry, what's the question again?
have you thought for your kinds of Oscar, yeah, the kinds of graphs that you're looking at, is this notion of hierarchical decomposition of interest to you? And is the nature of the work that you have something where you would want to have a data partitioning function or a graph generation function?
I guess for me, personally, for my application, I think I'm more interested in the graph generation. But I guess later on, for other application like DMRG, they will have to worry about the data partitioning too. So I need to look more carefully into that. Maybe Oscar or someone else have more insight into DMRG. Or YL, for example.
So the data partitioning and the graph generation, I guess in the context of linear algebra is what we're probably going to be more interested in. And the hierarchical part, I keep thinking of how to tie this to the switch eventually from a high-level task parallel to a low-level data parallel implementation. So that's the part where I would be interested in understanding a little more how to do that.
Say that again, which part?
So the making the switch from a task parallel once you've done the decomposition to now switching to a data parallel part where you're not breaking into tasks anymore, but just using standard data parallel SIMD-like constructs to actually do the final level of work.
So in many cases, that's just the implementation that the user supplies in their implementation of a function,
right,
or some library that they call.
But
in some other cases, there may still be a data partitioning step that basically says, at this level of hierarchy, I was handed something that's a huge subtensor or submatrix, and I'm going to further tile it into pieces and then invoke the same work, because the work can be done independent of the amount of data or which data, but I'll do some more breaking up of the problem and then hand that off to the make the respective calls with the appropriate data parameters. And that, by the way, is also something that Legion does, right, Mike?
Yes.
Here, whenever something is applied in an element-wise fashion, it can be pretty trivial to just describe here's the chunk of data to apply that to. So is that part of what you were talking about, Wael?
Kind of. I mean, I guess I'm slightly. I'm not quite sure I fully understand how the data locality aspect will play into all of this. So if my function assumes a certain data locality, either locally or globally, and now the partitioning part, if they're not talking the same language, then that may be an issue.
Okay. Well, why don't we go next? You had a few. I'm going to stop sharing. And Dimitri, you had some slides, and Mike, you had some content here. So Dimitri, you want to go for it next?
Sure. Can you see the slide?
Yep.
Okay. Can you hear me well?
Yes, we can hear you, and the slides look good.
Great. So I'll be brief. So ExaTensor, for those who don't know, probably most. So exatensor is the numerical tensor algebra library for dense, block sparse, and hierarchical tensors. And this is the last part, which makes it kind of interesting to look in some things like hi-hat. So the data structure, the main data structure in exatensor is a tensor. And it's inherently recursive. So the tensors are recursive here. And the depth of the recursion can be regulated by the user, but in general, so you can just vary the how much the depth of the recursion here. But in general, for example, right now the recursion stops at the node level, which is not very appropriate for heterogeneous nodes. So essentially, at the node level, the recursion stops, and at the node level, the tensors, or at least the parts of tensors which arrive there, they look dense. Consequently, then the basic workload illustrated in this slide for tensor operations is that so there are these purple tensors A0 and B0 which arrive on the node. And then there is some transformation needs to be done with them, transpose, compression, unpacking to some temporary location. And then there is some binary operation, for example, just something like tensor contraction or some other operations. And then so some accumulation back to the permanent location. And just memory management with allocation of temporary resources and destruction of temporary resources, which is done through custom allocators. So this is just the basic, very simple workload, what it's doing now. So then, obviously, at this level, at the level of the shallow recursion, which stops at the node level, you can also do some pipelining to try to optimize things, but that's not much interesting in this context. So so now if we have multiple devices and we still have shallow recursion, so which means that our tensors are dense at the node level, then we may need to actually decompose these tensors into parts and decompose it the way that is appropriate for the device to where the operations operating on these parts will go. Consequently, here this is like one case where we have, like, for example, some dense data structure, and we need to we need to decide how to partition it appropriately for each device, and how to do then the scheduling across multiple devices such that the whole thing gets executed optimally. But so the most interesting case that I'm looking for to implement and to use some kind of tool for that, like for example based on hi-hat, is the deep recursion case, where the recursion doesn't stop at the node level. So in this case, the tensors which live on the node, they still have a hierarchical structure. So they are composed of tensors. And this can actually repeat by multiple layers. So their parts can also, which are tensors, they can also be composed of tensors. Consequently, the data decomposition here is already defined by the application, meaning that the recursive tensor structure is defined by the application, and the data partitioning function, which partitions tensors, is provided by the application. With some adjustable parameters. And the work generation function here, it's actually just, it's guided by the data partition function, meaning that once data is partitioned, the work generation just looks up how the data is partitioned and splits the original parent task into subtasks based on the existing data partitioning. And in this case, we end up having like many smaller child tasks with dependencies, obviously, here. And so we need to aggregate them. So we need to somehow tend to schedule this aggregated graphs across multiple devices on a heterogeneous node. And here, the illustration here, so this is, for example, if I take a matrix as a specific case of a tensor, then this is just illustration of recursion, where just you have a dense matrix, then you have a matrix split into 4 parts, and then recursively into 16 parts, and so on. So this is like the basic storage of tensors in Exatensor, but in much more in more dimensions than just a matrix, and also with the block sparse tensors. So that's that's I'll be brief because time is gone.
Okay. Any other questions on this? Thanks. All right, Mike, you want to jump in with yours?
Sure. Let me share my slides here. Okay. Let's see. Can everybody see the screen?
Yeah.
All right. Okay. So I think the motivation for this talk is not so much to describe a solution so much as a problem. And that is effectively a number of months ago, we had a meeting where we were discussing hierarchy and the effects of hierarchy in various forms on how we might want to build a tasking system like Hi-Hat. And I think during that meeting, I, along with several other people, in my mind, was this problem of how we deal with bigger applications like adaptive mesh refinement. And so CJ invited me to sort of give a little summary of some of the things that I've been thinking about, and also, I'll mention that a lot of this is stuff that I've learned via many conversations with people at the national labs. And so I want to provide sort of perspective on various hierarchical challenges that occur in the case of AMR, and I will offer some solutions that we're thinking about and have already done in terms of addressing these problems in Legion at the very end. But mostly what I want to do is sort of describe the problem. And so you can think of this as like a case study in describing sort of some of the challenges that we have to address when building programming systems to target big machines and the kinds of applications like AMR that need to run on them. Okay, so for those of you that are familiar, this is going to be like a little mini primer on AMR. So science is becoming more expensive, right? Our details are getting better, more refined, and we're getting bigger machines that generate more data, right? And so scientists are realizing that they can only sort of simulate, the things that actually matter. You can't be simulating at full precision everywhere in your simulation. It's just going to take too long. It will not be scalable. And so what you do is you have to react to your simulation in some way. It has to dynamically react to your model, right? And there are two ways that people tackle this problem. One is with unstructured meshes, where you try to have unstructured meshes that are much smaller cells closer to the areas of interest, and then much bigger ones farther away. And you can they tessellate these, based on interesting shapes, depending on whether you're doing things in 2D or 3D. And the alternative is to do it with a more structured style, which is sort of have structured meshes with grids and stuff, but have hierarchical meshes in order to capture the refinement. And so I'll be talking more about this second approach. The first approach is interesting too, and is definitely very widely used as well. But I'm going to be talking more about the structured version, the AMR version today. Okay, so there's a bunch of AMR libraries out there, and I encourage you to go look at all of them. AMRX, which is based on the library formerly known as BoxLib, Chombo and Samurai, and some of the other, there's a bunch of other AMR libraries out there in the world, but these are just 3 that I picked from National Lab that I've sort of talked with the developers of at various points, trying to get a feel for how they do their AMR and how they do how they build their libraries to actually implement AMR. In particular, these libraries get used for doing lots of interesting physics, including combustion, astrophysics, nonlinear fluid flows. And the thing that's really interesting about these is I think these developers have really done a good job of building libraries to actually solve these problems, so that when you want to write a new AMR simulation, you don't have to rebuild everything from scratch. You sort of build up components of these AMR libraries together to build to get the simulation that you want. Okay, so how do these AMR libraries work? I'm going to be talking mostly today about patch-based AMR. There's also some other kinds of AMR, but this is mostly, the version I'll be describing is one of the more challenging ones, which is called patch-based AMR. And the way that patch-based AMR works is that you start with sort of a regular mesh at level 0, right? It's a regular grid, 2D, 3D. You can actually do higher dimensions, but 3D is usually pretty standard. As you get inch-string behavior in your simulation, such as shock waves or flame wavefronts for combustion, your grids will refine themselves in order along the area of interest in order to track it more precisely. And so what you get these refined levels of your simulation where you may have subcells to correspond to these levels of refinement. And you can recurse, up to 7 to 8 levels in order to capture really, really interesting behavior. Like when you've got a shock wavefront propagating, you really need to zoom in very close in order to keep your simulation stable. If you try to take too big a time steps on too big a cell, your simulation can become unstable very quickly if you're not properly refined. It's usually pretty standard that cells refine about 2 to 1 as you go down each level. In some cases, they will actually go down 3 to 1 or 4 to 1. But most commonly, it's sort of like in each dimension, you take a cell and you divide the distance in half and make subcells. Importantly, these refinements do not have to properly nest. So in the little picture up here on the upper right, you notice that there's a refinement at level 2 that actually is, sort of has cells that are subcells of cells from 2 different refinements at level 1. And so it's not actually a proper tree here. We actually have sort of like a DAG level or DAG style, level of refinement. And this makes life very interesting when it comes time to thinking about dependencies between the kinds of tasks that we're going to end up launching. The other thing that I'll point out here is that as you get to these lower levels of the memory hierarchy, the lower levels of this refinement, the lower levels actually require much, much more data in order to fill up the. They're going to consume much more data in terms of filling up the machine, because like every one of these levels, effectively can consume, can actually be much, as you go down the tree, you get more and more data usage at each of the different levels. So the top level simulation is actually very not memory intensive. And as you get farther down, there's more and more memory pressure from the additional data required by the additional levels. Okay, so what operations get done on these different levels and what computations are being done? Well, simulation was the most important part because that's what we're actually trying to compute. And that's mostly done on the lower levels. Sometimes it gets done on the intermediate levels to help with some of the smoothing, but mostly it's done at the very bottom of the AMR hierarchy. So whatever level is the finest level for a particular cell, that's where most of the simulation usually happens. And then what happens is, in order to sort of like take larger time steps and keep things stable, you often what you do is you interpolate up the tree. So you sort of have to take your cells at a lower level and interpolate up. I'm actually doing it backwards. Restriction goes. I'm mentioning it backwards. Restriction, because I get these confused. Restriction and projection go up the tree. So you effectively take your finer cells and you sort of have some sort of merging function that computes, the value for some physical value at a coarser level by combining those levels, the cells from the level below as well as the neighboring cells. And then you do some smoothing steps at that particular level, and you can go all the way up the tree like this, and then eventually you have to come back down. Right, you do interpolation and prolongation, where you actually sort of interpolate values for the finer cells from the coarser cells. And of course, I've mentioned here that on both the restriction and projection and the interpolation and prolongation, you can get all sorts of nasty boundary conditions that you really have to deal with. And different AMR simulations have different ways of dealing with the boundary conditions. It makes it really challenging because sometimes, different simulations will want different ways of dealing with those boundary conditions between grids that are either refined or not refined. Especially like, for example, let's see if you can see my mouse or not, between like these cells on a border, right? The interpolation can get really complicated in terms of figuring out what neighbor dependency cells you need to actually look at from both your level as well as the level above or below. And so that makes the dependence analysis for these kinds of computations really, really hairy. And really challenging for application developers. And the libraries fortunately handle this, but they don't always handle it particularly well today. Okay. The next part of AMR is I sort of told you about the operations, how they get composed together. Well, what you're actually doing really with this smoothing is effectively you're doing like a multi-grid sort of solve on top of this AMR hierarchy that you've constructed. And so they actually do run things like V cycles and W cycles and full multi-grid cycles of going up and down these levels of the hierarchy in order to smooth out the data for the AMR simulation. And oftentimes, what really makes this interesting is the pattern of cycle that you choose is often data dependent based on how your simulation is running and your convergence on some of your iterations in order to figure out how quickly you're converging to the next time step. And so oftentimes they will dynamically decide what to do based on the data that they're doing or the data that they're computing on and how the convergence is occurring. Another interesting property of these different smoothing levels is that oftentimes you can have smoothing being done for different physical processes in parallel. So in multi-physics applications, you can actually have smoothing happening for multiple different physical quantities at going on at the same time. And so that creates even another level of task parallelism that you get by having multiple smooths happening at different levels of the tree at different times. You can often also use like custom libraries like Hyper or Trilinos to help implement some of these solvers, but a lot of the AMR libraries actually come with their own solver or own smoothers sort of built in, and it really depends on the library as to which one whether you're using sort of an external one or your own built-in one. Okay, and then the last thing I'll mention is that to make this even more complicated, today a lot of these AMR libraries are moving in a direction where they also need to provide uncertainty quantification. This is the idea of uncertainty quantification is you need to capture the sensitivity of your simulation to how the actual or how sensitive it is to various input parameters to the simulation. So is your simulation going to depend on various knobs or inputs, and if so, how sensitive is it? It gives you a feel for how accurate your simulation is, and how likely it is to be stable versus unstable, contingent on various input parameters. And so uncertainty quantification, you oftentimes what you do is you'll play the simulation multiple times forward with different perturbations in the inputs. And I'm very much glossing over how this works, but there's a lot of detail and math to this. But effectively, you perturb your inputs a little bit and try to see how the simulation reacts to it, and from that you can infer sort of how stable it is. Sometimes they even play the simulations backward. A lot of physics can actually be if you can play it backward and show that you get back to the same initial conditions, that's actually a very good sign that you're pretty stable. But that approach can actually be much more memory intensive, and so it's really a trade-off there and complexity and memory pressure cost to see what kind of uncertainty quantification you want to do. And yeah, the end result here is that we actually may have multiple different, from our perspective, is we actually want to have multiple different simulations possibly running in parallel, all on the machine at the same time, and this makes things even more challenging. Right, and so I want to pull out sort of three kinds of hierarchy that we notice in these simulations, these AMR simulations, and then I'll talk a little bit about them in more detail. So first is we have hierarchy of data, right? We have multiple different levels. Notice these levels are actually, even though they're usually represented discretely, right? So each level is not like just a logical refinement. It's actually a physical allocation of data separate from the level above it. And so we're not just like recursively tiling, sort of similar to how we would do for like an array-based computation. These levels are actually just distinct. And so we have, multiple levels of our simulation data. We have a hierarchy of computations, right? We have computations that are nested, right, with our different cycles for the smoothers across different levels of the AMR simulation, right? And we have a hierarchy of software too, right? UQ is sort of our outermost layer of software, and then we have our AMR simulations, and then inside of those we're doing multi-grid smooths in order to keep things stable, right? And I think one of the important takeaways that I got learning a lot about AMR is that there's sort of a mismatch between the hierarchy of data and the hierarchy of computation. And what I mean by that is that it's not always true that the topmost computation, sub-computations are using a subset of the data of their parent computation. Right, that's not actually true here because, right, like for example, if you're looking at a smoother, the smoother is just working on one particular level, right? And even though that smoother may then recursively launch off subtasks that handle the sub chunks of a level above or below it, right, those levels above and below are actually discrete chunks of data from another memory allocation, right, for a different level. And so if you tried to specify this as a functional program, right, you'd actually have trouble. You have to pass in a whole bunch of levels to the topmost task that it wouldn't actually process, but it would instead just sort of hand down to the subtasks. And I haven't even mentioned memory hierarchy here, which is a whole other problem. I've mainly been focusing here on the hierarchies or hierarchy problems that actually occur in software. So I'm gonna talk. Let's see, how much time do I have left? I guess I've got a few minutes, so I'll just mention these very briefly. I guess, sort of elaborating on these things, very quickly. I'm going to skip the Legion parts, but hierarchy of data, the biggest problem that these AMR developers have is memory pressure, right? Even more important than load balance or anything like that, they have trouble with keeping things in memory, right? Because when you get a refinement, that sort of explodes out a new allocation memory on a particular node, wherever that or nodes wherever that refinement occurred, and they may have already been close to being fully utilized in terms of memory, and then you may have to distribute that refinement to a different node. So when you're regridding, you have to repartition your data often on the fly in order to redistribute your memory just to keep you from running out of memory, just to keep your simulation alive. And this is actually an incredibly hard problem for them to deal with, because when you repartition, you have to think about all the locality that happens, not just within a level, with nearest neighbors and stuff, but also the locality between your partitions of your parent level and your child levels, and how they've been partitioned and how their data has been placed. This creates a lot of problems for them. And so what you really often want to have are multiple dynamically created logical partitions of your data, so that you can partition it in lots of different ways, and then have the ability to place it in lots of different ways based on the machine and the state of the machine, and how much memory pressure you're feeling. And so, Legion has some solutions. I'm going to skip those for now, just so I can get done with it, finish the talk. We also have hierarchy of compute, right? Our computations have to be specified hierarchically in terms of launching tasks and subtasks. The multi-grid cycles tend to create really nice subtasking possibilities. And it's really easily expressed as a recursively divided problem. But again, you get this unmatched memory hierarchy problem that I described earlier, where the data doesn't necessarily correspond to the tasking hierarchy. And so you often want your tree of tasks to match your machine, and then you have to have some way of specifying the data dependencies for those tasks that help things get hooked up properly. And finally, I'll mention hierarchy of software. These packages are huge. They're not going to be rewritten or not completely rewritten. And they need to interoperate with each other. And they don't provide, natural interfaces for interoperating with each other very well. And so really, this is where you want some level of implicit parallelism to discover the graph and do the dependence analysis for you. Because you really need to do that dependence analysis across abstraction boundaries, and not just, not just within inside of a particular application or library. And so you need to find those dependencies and task parallelism that exists across libraries, and not have to put in big barriers and stuff between them, because barriers don't work. Barriers work pretty well when your levels of software, go A, B, C, but they don't work well when they're composing with each other, and have like one library that works inside of another library, inside of another library, and so forth. And I've got Legion solutions. I'll push slides out to everyone so you can look at those later. So anyway, to wrap up, AMR is really hard. There's lots of kinds of hierarchy that we have to deal with. It creates a lot of problems for our tasking infrastructure. And it makes building these kinds of systems really hard. And I think, as people building programming systems, we really need to think hard about these kinds of challenges that often don't get captured by things like mini apps and stuff. So with that, if there are questions, I'm happy to take them. I'll be here for a few minutes, but I realize it's probably 10 o'clock now.
Thanks, Mike. And I did post these slides, and the other slides too that we were talking to earlier are posted, and we're essentially, the next step of this is we're trying to figure out sort of who cares and what actual infrastructure do we need to support this. So if you're more interested in continuing or joining that conversation, let us know. Thank you.
Yeah, thanks, everybody. Let's wrap it up on time. Thanks a lot.
Have a good one. Bye.
Have a good one. Cheers.